This PowerPoint presentation covers the topic of predicting precipitation from section 15.1 of our textbook. Predicting whether a solid will precipitate from solution depends on knowing whether the concentrations of ions in solution will exceed their maximum allowed solubility values. This essentially means comparing the Q value to the KSP value. If the product of the current concentration values is less than the KSP, then you have an unsaturated solution and no solid will form. Furthermore, if any solid is present or is added, it will dissolve. If the product of the current concentration values, the Q, is equal to the KSP, you have a saturated solution. The solution contains the maximum amount of dissolved ions. The system is at equilibrium and no net dissolution or precipitation will occur. If the Q value is greater than the KSP value, however, the solution is supersaturated and precipitation, or the formation of solid, will occur until Q is equal to K. Let's look at an example. If 20 milliliters of 0.1 molar magnesium nitrate are added to 50 milliliters of 0.1 molar sodium carbonate, will magnesium carbonate precipitate? The KSP of magnesium carbonate is 6.82 times 10 to the minus 6. So let's draw a little picture of what we have. We have a beaker of sodium carbonate, which is going to contain sodium ions and carbonate ions. And we're adding a solution of magnesium nitrate that has magnesium ions and nitrate ions. When we put these two solutions together, you'll have magnesium ions and carbonate ions in the same space, and the question is, will a precipitate form? Let's start by writing the dissolution reaction for magnesium carbonate and its KSP expression. And I'm just going to put in a reminder that these concentrations are the equilibrium values. To figure out whether or not a solid will form, we need to know whether the Q is greater to, equal to, or less than the K value. Remember, Q has the same form as K, but the concentrations are not necessarily at equilibrium. They're at some time t. So let's evaluate Q. We need to figure out what the concentrations of magnesium ion and carbonate ion would be when we mix the two solutions together. Notice that we're doing two things. We have an original volume and concentration of magnesium ions, but we're mixing that with another solution. So we're going to have to figure out the new concentration of magnesium ions. We start with 20 milliliters, which is 0.02 liters, of magnesium nitrate. and has a concentration of 0.1 molar. There's 1 mole of magnesium ions per mole of magnesium nitrate. So this gives us the moles of magnesium that we're putting into our solution. We need to divide that by the new total volume, which is going to be the 20 milliliters plus 50 milliliters, or 70 milliliters. So the concentration of magnesium ions is going to be 0.0286. Let's do the same for the carbonate. For the carbonate, we're adding 50 milliliters of a 0.1 molar sodium carbonate solution. Again, there's 1 mole of carbonate per mole of sodium carbonate. And we're going to divide that by the new total volume, which is again 70 milliliters, to get a concentration of carbonate that's 0.0714 molar. So we have our concentration values of the two ions that would exist if we pour these two solutions together. So let's go back and evaluate Q. We said Q would be equal to the concentration of magnesium ions times the concentration of the carbonate, and when we multiply these together, we get 2.0 times 10 to the minus 3. And again, that's our Q value. We need to compare Q to K. Going back up here, we saw our K value was 6 times 10 to the minus 6. So our Q is larger than K. That means we have too many ions in solution. We need to get rid of some of those, and some solid will form. We've just seen that if you add 20 milliliters of 0.1 molar magnesium nitrate to 50 milliliters of 0.1 molar sodium carbonate, the concentrations of ions in solution will exceed their solubility limit and some solid will form. Let's look and see if we can figure out how many grams of the magnesium carbonate solid will actually form. Let's write the equilibrium equation again. We could set up an ice table with our initial concentrations of magnesium and carbonate ions from the previous problem. We've already seen that this reaction will have to proceed in the reverse direction to reach equilibrium. So we would have minus x for each of our products. We're not showing values for the magnesium carbonate because it's a solid. We could set up a KSP expression. This would result in a quadratic equation, which we could solve. However, we can use a trick from chapter 13 to make the math a little bit easier. We notice that the K value is quite small, and we're starting with mostly products. And we know the reaction has to proceed in the reverse direction. So we wouldn't be able to assume that the X values were small, but if we use stoichiometry to drive the reaction back to reactants and then let it adjust forward, we'd probably be justified in letting our Y values be small. So let's go ahead and make this into a stoichiometry step where we're going to let the reaction proceed backwards to its full extent. We see that magnesium ions are the limiting reactant, so we'll let our X be equal to 0.0286 to let the magnesium ions go down to 0. The carbonate ions will be 0.0714 molar minus 0.0286, which gives a value of 0.0428. Again, that's if we let X equal 0.0286. Of course, this can't be equilibrium because we have 0 for our magnesium concentration. So we now need to do a new change row and finally our equilibrium. So the reaction will proceed forward to produce a little bit of magnesium and a little bit more of carbonate. So our new expression is 6.82 times 10 to the minus 6. The K value is going to be equal to Y times 0.0428 plus Y. We'll try assuming that Y is small in this term, and we can solve to get a Y value of 1.59 times 10 to the minus 4. Which again would be equal to our magnesium ion concentration. Okay, were we justified in assuming that Y would be small relative to 0.0428? Yes, when we do the percentage on that, and if we take 1.59 times 10 to the minus 4, divide it by 0.0428, and multiply by 100, we get about 0.4%. So our assumption was valid, and we can go forward with this Y value. Okay, so that tells us that at equilibrium, we'll have 1.59 times 10 to the minus 4 molar of the magnesium ion and about 0.0428 molar of the carbonate ion. But what we really wanted to find out was how many grams of magnesium carbonate would form. So the total amount of magnesium is going to be split between magnesium carbonate and the magnesium ion. We know that we started with 20 milliliters, or 0.02 liters, of 0.1 molar magnesium ions, which means we started with 0.002 moles of magnesium. Some of that is staying or is going to be as magnesium 2 plus. The rest will be converted to magnesium carbonate. So if we take that 0.002 moles of total magnesium and subtract the moles of magnesium that are staying as the ion, this is going to be 70 milliliters of 1.59 times 10 to the minus 4 molar, or 1.113 times 10 to the minus 5 moles, that will be in the aqueous form. Subtracting these, we get 1.98, 1.989, times 10 to the minus 3 moles that will be as magnesium carbonate. How many grams would that be? We need to take the moles. Use the molar mass, which is 84.32. And we find that we should get 0.168 grams of magnesium carbonate solid forming. Example 5 asks, the KSP of magnesium hydroxide is 8.9 times 10 to the minus 12. What concentration of hydroxide is needed to start precipitating magnesium hydroxide solid from a solution that is 0.0537 molar in magnesium ions? Again, we'll start by writing the dissolution reaction. We're given that we have a solution that contains 0.0537 molar in magnesium ions. We know the KSP, and we're asked what concentration of hydroxide will just start the precipitation. So we're looking for the concentration of hydroxide where we just have a saturated solution. So when Q will be equal to K. So in terms of our K expression, we know that the concentration of magnesium ions times the concentration of hydroxide ions squared should be equal to 8.9 times 10 to the minus 12. We already know the concentration of magnesium ions, so we could solve this expression for the hydroxide concentration that would be needed to just start precipitation. So when the hydroxide concentration is 1.29 times 10 to the minus 5 molar, then the Q value, the concentration of magnesium times the concentration of hydroxide square, would exactly equal the K, and that's the minimum amount of hydroxide you would have to add before you would start to see precipitation. Any additional amount will form precipitate. Question 6 asks us to consider a system with more than one possible precipitate. Hydrochloric acid is slowly added to a solution that is 0.1 molar in lead 2 plus ions and 0.01 molar in silver plus ions. Part A asks which will precipitate first, silver chloride or lead 2 chloride? To answer this question, we need to know the KSP values of the two proposed solids. The KSP of silver chloride is 1.77 times 10 to the minus 10. The KSP of lead 2 chloride is 1.17 times 10 to the minus 5. Notice that the KSP value for silver chloride is much smaller than the KSP value for the lead 2 chloride, and so we expect silver chloride to precipitate first. Question B asks, at what concentration of chloride will silver chloride start to precipitate? We see that the KSP of silver chloride is 1.77 times 10 to the minus 10, and that this would be equal to the concentration of silver ions in solution times the concentration of chloride. Again, remember that KSP represents a saturated solution. So when the concentrations are less than that value, you won't get precipitate. We're actually looking for what chloride concentration would just give us precipitation. In other words, would just get us to saturation. So like we did in the previous problem, we could solve this equation for the chloride concentration divided by the silver ion concentration, which we know in this problem. So this result shows us that we'll start to see silver chloride precipitate when the chloride concentration in solution reaches 1.77 times 10 to the minus 8 molar. What level of chloride in solution is needed to cause the precipitation of lead 2 chloride? We would do a similar process, except use the KSP for the lead 2 chloride. Notice in this equation we have chloride squared, however, so when we solve for the concentration of chloride, we're going to have to take the square root. Our lead 2 plus concentration was 0.1 molar. And we find that the chloride concentration has to get all the way up to 0.0108 molar before we start to see any lead 2 chloride precipitating. Notice the large difference between these two numbers, which justifies our original conclusion that the silver chloride will precipitate first. Finally, question D asks, when you start to see the first lead 2 chloride precipitate, what will be the concentration of silver ions in solution? So we said that we're looking at a chloride concentration that will get the lead 2 chloride to precipitate to be 0.0108 molar. If we go back to the KSP expression for silver chloride, and solve it for silver ion concentration, when the concentration of when chloride is 0.0108 molar, the silver ion concentration is going to be 1.6 times 10 to the minus 8 molar. Why would we be interested in this number? Remember that we started with 0.01 molar of the silver ions, and 0.1 molar of the lead 2 plus ions is what we started with. As we add hydrochloric acid, the first chloride is going to react with the silver ions and start to precipitate that out. So we'll see the formation of silver chloride. And as that's happening, the amount of silver ions in solution is going to decrease. We can remove almost all of the silver ions from the solution before removing any lead ions. This is called selective precipitation. We started with a solution that had large concentrations of both ions. By adding chloride, we can precipitate out the silver chloride, almost all of it. We went from 0.01 molar down to 10 to the minus 8 molar, which if you do the math on that is 99.9998% removal. Before you start to remove any of the lead 2 plus ions. Silver is a valuable commodity, so the silver ions can be removed and collected as silver chloride, and the silver can be regenerated. So we've talked about how to determine whether a precipitate will form and how much will form. You should now be ready to do group problem number 6 from this chapter. The next video in this series will look at the common ion effect.